Okay, in this video here, I'll whip through 3 of the 1H application problems. We've got an enclosure, sort of one of these L-shaped enclosures, and the perimeter is 160. So 160 equals that, and that. This bit here we're going to note is y take 20. This bit here is x take 12. Now, if I'm working out the perimeter, I can add all of these little pieces together, or I can note that this distance here and this distance here is just another y, this distance here and this distance here is just another x. So it's going to be 2 lots of x plus 2 lots of y. Now, we need to write a rule for area. So A of x, the area, is equal to x by y. Remove this little bit here. So that's going to be x times y, remove 12 by y take 20. And what we want to do is make it in terms of x. So what we'll do over here is we'll make y the subject. 2y equals 160 take 2x. Y is going to be 80 take x. So now we've made y the subject, it allows me to pop 80 take x where I see y. So it's going to be x equals x, 80 take x, take 12, 80 take x, take 20 is going to be 60 take x. And there's my a of x, my area function. Okay, state a suitable domain of the function a of x. All right, so what's going to happen here is this one here, so x take 12, that's going to be more than or equal to 0. This bit here is going to be more than or equal to 0. So that means x has got to be greater than and equal to 12. Okay, so the value of x is going to be greater than or equal to 12, otherwise this goes negative. No, that's wrong, is it? Yeah, it's got to go, it's got to be more than 12, because 12 take 12 is equal to nothing, which means we have no kind of L shape on it. But if it's more than, so say 13, 14, 15, it's going to be like 3, 4, 5, and just start increasing from there. So it's going to be greater than 12. What about this one here? Well, y take 20 similarly has got to be greater than and equal to 0. That part there, it's got to be greater than and equal to 0. Now, because y, we found y in terms of x, what we can do is just bang 80 take x in there. So 80 take x take 20 has got to be greater than or equal to 0. That means 60 take x has got to be greater than or equal to 0. Negative x greater than or equal to negative 60, x less than 60. So this is implying that a suitable domain for the function would be x is an element between 12 and 60. Now, this graph here is going to be some sort of inverted parabola graphed over the domain of 12 to 60. So what I would probably do is, come on, Shift 7, define f of x equals x times 80 take x, take away 12, 60 take x. I'm going to do f of 12, that's 240. So a of 12 equals 240, and a of 60 probably will be pretty similar. Oof, okay, didn't predict that very well. Okay, and what's going to happen, I'm predicting, is that, so you're going to pop 12 in and you're going to pop 60 in. It's going to be 240 and probably 5 times as high, so somewhere up there and somewhere down there. And I think what will happen is it's going to go like that in between. Okay, So what we're looking for is the value of the turning point. And I think what we'll do is let's have a crack at Fmax. So what we're going to do is calculation Fmax here. Now the expression we want to operate on is f of x. So we'll go shift and 8. And it's between 12 and 60. So this basically says, hey, can you go hunting between 12 and 60 on this function here and tell me the highest value? And it goes, yeah, my highest value is 1396 at x equals 46. So 46, it's 12, somewhere around here. I mean, this is the world's worst graph. It's not to scale at all. What was this one? This was 1200, so it's going to be a bit higher than that. So let's pop it down there and draw something parabolic looking between there. 46, 1396. So find the maximum possible area of the enclosure. So it's 1396 meters squared. The value of x is equal to 46. The value of y is 80 take 46, which is 34. Okay, so these are the values that produce this maximum area. All right. Cuboid tank is open at the top, noted, and the internal dimensions of its base, x and 2x, height is h. The volume of the tank is V meters cubed, and the volume is fixed. Okay. The S meters squared denote the internal surface area. So let's just get the surface area first, which is, so it's got an open top, so it's going to be 2x by h. That front part there is 2xh, plus the back part there is another 2xh. These side bits here are going to be xh and xh, so that's another 2xh. And finally, the bottom part there is going to be 2x squared. S equals 6xh plus 2x squared. Okay, so find S in terms of x and h. Done. Find S in terms of V and x. Well, the way we're going to get a V is work out the volume. So volume equals length, width by height. So 2x squared h is the volume. Now what I'll do is I'll make h the subject of this, so I can bang in a value for h, which will be v and x, and this will be in terms of v and x. So it's going to be h equals v on 2x squared. Now let's pop that definition of h in here. So s equals 6v over 6x vx over 2x squared plus 2x squared. One of those x's cancels with that once, 3 times. And we've got s equals 3 on x plus 2x squared. Okay, so state the maximal domain for the function defined by the rule in part A2. Okay, the maximal domain. Well, I think it's just going to be, so this is A, find S in terms of that, so this is part 1 here, part 2 here. B, I think it's just x is an element. Can't pop 0 in because that will be undefined. It's going to be 0 to positive infinity, I think. If x is between 2 and 15, find the maximum value of s if v is equal to 1000. Okay, so C, we're going to go, oh, I forgot the V there. So yeah, that's part 2. So sorry about that. It's like, yeah, I forgot to put the V in. So that's going to be S equals 3,000, 3 lots of V, where V is 1,000, over X plus 2X squared. And what we want to do is find the maximum value between these two values. So again, I think the way I would do this is I would define this as a function, 3,000 over x plus 2x squared. And let's just see how it's going to behave. So this is like a hyperbola added onto a parabola. This is a hard one to visualize. Oops, hard one to visualize. So we got a hyperbola and a parabola. So you could sort of get an idea of what this will look like with addition of ordinates. So it's going to be a... I'm struggling here. So I think the best bet is to just run an Fmax on this and find the maximum value of S when V is 1,000 between these two. So let's go ahead and do an Fmax for the function between 2 and 15. And this should lock onto a value. So it happens at 2. So I think it's going to look hyperbolic, because I think if you look at like they're really large values onto a small value. So I think what's going to happen is it's going to go down like this between 2 and 15. We'll have a look at the function in a sec, but yeah, I think that's what's going to happen. So max val is 1508. What's the unit? It's meters squared. Okay, so noting that that's our domain, so we want to graph this thing. So I'll just go into the graph and table and adjust my Cartesian planes so that it goes up by a massive amount. Between 0 and, let's go 20. Okay, so you can see what happens. So yeah, it goes down and then it kicks back up again. So it sort of looks hyperbolic. And what happens at this point, or at some point, is the parabola, this parabola here, takes over as like the higher function, and it starts to kind of look parabolic from this point here. At this stage of the course, you really shouldn't know that that's the graph, and you can see here, I've taught this for a few years now, and you know, I didn't anticipate that that's what the graph would look like. So, CAS style question. All right, so the last problem, let's see, did I answer the question? If it's between 2 and 15, find the max value. Yep, that answers the question. All right, this last one here, we've got a function defined between 0 and 6. Okay, so it's a hyperbola. We've got a rectangle, and what we're going to do is find the area of this rectangle. Okay, so these are really common problems. So the typical approach will be, okay, so that coordinate there, the x value is a, i.e. I don't know, and the y value is f of a. So it's going to be a, f of a, which is a and this, which is 6 over a plus 2. So I've just popped a into f of x. Now to get the area, it's going to be this value here by this value here. So the area, I'm going to call it area of, or a of a equals a times the y value here, which is 6 over a plus 2, which is 6a over a plus 2. All right. Now, state the implied domain and range of A. All right, so what can't we do? Well, we can't pop in -2. So it's going to be greater than -2. The value of A, so A has got to be greater than or equal to 0, I think, is it 0? Yeah, 0. Okay, so it's got to be greater than or equal to 0. So I think what's going to happen is, so this is A, this is A of A. When A is equal to 0, we get 6 multiplied by 0, which is 0, so it starts here. And what's going to happen is it's going to start to climb at that point. Again, I don't really know what the graph looks like, other than to say that as A increases, let's just try it. 6 times 2 is 12. 12 over 4 is 3. So when A is equal to 2, A of A is equal to 3. Okay, and you can see basically what's going to happen as A increases, this one is going to be larger than this one. So it's going to grow. I don't think it's going to grow linearly. I think it's going to sort of be like this. Okay, but again, I'm not 100% sure. So the implied domain is going to be when A is greater than or equal to 0. I think they want it as A of X. So yeah, it would be X is greater than 0, but you can call your function whatever you want to call your function. Okay, so this is B. This is A here. State the max value. So you can see that the max value, if this is the domain, is 0 to 6. What I'm going to do is bang 6 into the function, because that's where it's going to be at its highest at that point, remembering that it will continue towards positive infinity. So 6 is absolutely going to be the largest value. So A of 6 is equal to 6 6s are 36, 36 on 8, which is, oh my god, 18 on 4, 9 on 2. And yeah, it's going to look something like that. So my guess is parabolic, but it could be linear. Oh, I don't really know. Okay, 6. So let's go over to calc. Okay, let's go to the calc. So I'm going to shift 7, define f of x equals 6x over x plus 2. Now let's have a look at it. Actually, let's f max it first. Calculation. F max for my function, please, between 0 and 6. This hopefully says 9 on 2. Yeah. Okay, but the big reveal. Let's have a look at what the graph looks like. So f of x, let's adjust the values here. So between 0 and 6, let's go a bit higher. Actually, let's go 10. Max, I know at x equals 6, the y value was 9 on 2. Let's just double 9 on 2, 9, 10, 15. Let's go 15. All right, let's have a look. It's not parabolic. Right, so what happens is it actually looks like the sort of root function, actually. Yeah, that's what it ends up looking like. So you can see here that it increases to positive infinity. What happens is the growth rate starts to slow down. Okay, so it increases a bit quicker, and then it starts to slow down. So yeah, it will look like D, something like this at 0, 6, 9 on 2, and it's going to go up like that. Okay, so there's those questions there. This one here in particular, question 6, is a pretty common style of question.